Physics Part 398. Number 3. Only alpha particles that pass very close to the nucleus, almost striking it head on, will experience large enough repulsive forces to cause them to deviate through angles greater than 90 degrees. The fact that so few particles did so confirms that the nucleus is very small and that most of the atom is empty space. Because atoms, number 4, because atoms are neutral, the atom must contain negative particles. These travel around and orbit the nucleus. So atom is small, but nucleus is very, very, very small. And within the nucleus, we've got protons and neutrons, a very small mass, so to say. And then very, very, very thousands of degrees smaller than that are those electrons which orbit around the nucleus. So most of the atom is empty place. And that's the reason why the alpha particles went straight and there have been no deviation at all. Empty space. Most of the atom is empty space. Next we read number 4. Because atoms are neutral, the atoms must contain negative particles. These travel around or orbit the nucleus. The figure shows some of the possible trajectories of the alpha particles using the nuclear model of the atom and equations to describe the force between the charged particles. Rutherford calculated the fractions of alpha particle that he would expect to be deviated through various angles. Calculations agreed with the results from the experiment is confirmed the nuclear model of the atom. Rutherford calculated the diameter of the nucleus is about 10 power raised to minus 15 m, and the diameter of the whole atom is 10 power raised to minus 10 m. Figure shows the features of the nuclear model of a nitrogen atom. The diameter of a nitrogen atom is more than 30,000 times bigger than the diameter of its nucleus. The diameter of nitrogen atom is more than 30,000 times bigger than diameter of its nucleus. So the nucleus is 30,000 times smaller than the atom itself. Some years later, the alpha particles scattering experiments was repeated using alpha particles with high energies. Some discrepancies between the experimental results and Rutherford's scattering formula were observed. There seemed to be occurring because the high energy alpha particles were passing very close to the nucleus and were experiencing not only the repulsive electrostatic force but also a strong attractive force which appears to act over only a very short range. This became known as the strong nuclear force. This is the force that holds the nucleus together. Probing matter using electrons. Electrons are not affected by the strong nuclear force. It was suggested that they might therefore be a more effective tool with which to investigate the structure of atoms. As we saw in the previous chapter, moving electrons have a wave-like property and can be diffracted. If a beam of electron is directed at a sample of powdered crystal and the electron wavelength is comparable with the interatomic spacing in the crystal, the electron waves are scattered from planes of atoms in the tiny crystals.